So till now we have covered all the prerequisites which were required for understanding the modeling of epidemics, and we have looked at the two most important factors there. The first one is the pathogen and second one is the network. So we are now all set to go ahead and model the spreading of a disease. So let's see how we can go about it. So let's say here is a node, here is a person, and now this person over here, it has, let's say, 4 friends here as shown in this figure. So there is this person and this person has 4 friends here. And then these 4 friends, each of these have again 4 friends each. So you see, we are taking a very simple example for modeling. So we'll start from a very simple example and we'll move towards a complex network. So we are taking the most simple network, that is, which is in the form of a tree. Obviously, we know that social networks are not in the form of tree because there will be triads on this network and these nodes will be connected to each other, but only for the sake of simplicity, for the time being, we are taking the network to be a tree network. So one node having 4 children, each of these 4 children again having 4 children, and then each of these again having 4 children each. So this is the kind of network on which we'll be modeling our disease. So this is the network here. Now let's say this, if you see this edge over there, so I write a number on this 0.5. So as we have discussed previously, there were 2 factors. One was the network and another was the pathogen. So the network we have seen here is in the form of a tree over here. And second thing is the contagiousness of the pathogen. So we model the contagiousness of the pathogen in terms of probability. For example, I have given this edge a probability of 0.5. What does it mean? It means that if this node here is infected, then there is a 50% chance that this node will be able to infect this node. So with a 50% probability, 1/2 probability, the infection will transmit across this edge. And if this node is infected, this particular child will be infected. So I say that the probability of infection across this edge is 0.5. And again, for the sake of simplicity, I say that the probability of infection across all the edges is 0.5. So again, if this node is infected, it infects this node with a probability of 0.5. Similarly across this side, similarly across this edge, and similarly across all of these edges. So every edge has a probability 0.5 of infection. What can we say from here? So let me just take the first level of this tree. So I redraw this network here. I have this node which is the same node here. So I take this node here and then this node has 4 children and it can infect each of these. It infects each of these children with a probability of 0.5. Now if this node is infected, so I show it with a red circle. This node is infected. How many children do you think it will infect here? So each of its child, it infects with a probability of 0.5, and when it infects these, how many children do you think will become infected? So I redraw this network here just for the sake of simplicity, and my question is, how many of its children will it infect? Okay. So if we see here, this node has a 0.5 probability of infecting this node. What does that mean? That means that if I toss a fair coin here, an unbiased coin here, I toss a coin, I get head with a probability of 0.5, right? So if head turns up, I'll mark the particular child to be infected, and if there is a tail, I'll say that this child is not infected. So how do I model this? If the probability of infection is 0.5, I'll take a fair die, toss it. If I get a head, it means this node is infected, else node. And I do this for all of its children. So I do it for second child, and let's say I get a tail, and if I get a tail, this node remains uninfected. And then I do it for the third child, and let's say I get a head and I infect this, and I do it for the fourth child, and let's say I again get a head, so I infect this fourth child also. So 3 children are infected. So this happened for this particular case. what do you, so these three guys got infected over here. So what do you think happens on an average, on an expectation? So what is the expected number of its children which will get infected here? So let's quickly see that. So I again redraw it. Okay. So here I have 4 cases. In this case, I'm tossing a coin. Here I'm tossing a coin. Here. So 4 of these are different experiments which are independent of each other. So I have 4 experiments here. I toss 1 coin for this, 1 coin for this, 1 coin for this, and 1 coin for this. And all these coin tosses are independent of each other. So I say that these all experiments are independent. One has nothing to do with another. All of these are independent. And now our aim is to find the number of heads. Expected number of heads rather. So if the number of heads I get is equal to the number of nodes infected, because if I get a head, I infect that particular node. So our aim is to find the expected number of heads. So whenever we have to find the expected number of a variable, we model it in the form of a random variable. So I take a random variable x here, and the value of this random variable x is equal to the number of heads I am going to get. And how do I find the value of x over here? It is with the help of these 4 things. So what I do is, I take 4 more random variables, 1 random variable for each experiment. So for experiment 1, I have a random variable x1. Rather, we call it indicator random variable. So indicator random variable is a random variable which takes the value only 1 or 0. And then for E2, I have another indicator random variable. For E3, I have 1. For E4, I have 1. Indicator random variable is something very simple. What is happening in experiment 1? I'm either getting a head or I'm not getting a head. So I say that the value of x1 is 1 if I get a head and 0 if I do not get a head. So this is what do I mean by an indicator random variable. It is 1 for success and 0 for failure. So I have x1 which is 1 if head appears, 0 if tail appears. Similarly, x2 is 1 if head appears, 0 if tail appears, and same for x3 and x4. So now can you write this x in terms of x1, x2, x3 and x4? So what is my random variable x? It is the number of heads. So I know that x1 is what? The number of heads I get from experiment 1. Right? If it's a success, I get 1 head. If it's a failure, I get 0. Similarly, x2 is the number of heads I get from experiment 2, which again can be either 1 or 0. Similarly, I have x3 and then I have x4. So what do I can say is x equals to x1 plus x2 plus x3 plus x4. So wherever I get a head out of these experiments, I can add that value and it becomes equal to x. Okay. What is our aim? Our aim is to find the expected value of x. So I take an expectation on both the sides, left hand side and right hand side, and I get expected value of x is expected value of whatever is there in the right hand side, and I can actually distribute this expectation. So I can write expected value of this complete term x1 plus x2 plus x3 plus x4 as something like this. So this is called linearity of expectations. I won't go in much detail. Okay, so I get expected value of x as this, and then again here is a you can take it as a black box. So just understand this. If I'm talking about the expected value of an indicator random variable, so here x1, x2, x3, x4 are indicator random variables, either 0 or 1. So if I talk about the expected value of an indicator random variable, it is nothing but the probability that this variable is 1. So I can write it like this. Expected value of x is probability that x1 equals to 1 plus probability that x2 equals to 1 plus probability that x3 equals to 1 and so on. And then we know what is the probability that x1 is 1. When is x1 1? x1 is 1 when I get a head in the first coin toss, and the probability of that happening is nothing but 0.5, and same is for x2, x3 and x4. So overall I get the value 0.5 into 4, which is 2. So I've done it rigorously. Even if you didn't understand it, it's perfectly okay. It comes to us intuitively also that if let's say I toss a coin 4 times, so on an average how many heads will you get, and intuitively your mind tells you that the answer is 2, 0.5 into 4. So even if you didn't understand this calculation of expectations, it's perfectly fine. Okay, now let's take another example. Again I have a node here, and then this node has 4 neighbors, and then each of them has 4 neighbors, and then let's say the probability of infection across every edge this time is 0.25 instead of 5. So in the previous case we have tossed a coin. So the probability was 0.5, we tossed a coin, we looked at whether it's a head or it's a tail, and accordingly we did what we have to do. Now what I do in this case? Can I toss a coin in this case? I don't know. So coin gives me head with probability 0.5, tail with probability 0.5. What do I do in this case? So what we can do in this case is we toss a biased coin, and my biased coin is such that it gives me head with a probability of 0.25 and gives me tail with a probability of 0.75. So a biased coin is something like, it's not a fair coin. Fair coin gives you head and tail with equal probability. So a biased coin can be something like, if you remember the movie Sholay. So there was a coin which had head on both the sides. So that was a biased coin. In that case, probability of head was 1, probability of tail was 0. No matter whatever you do, you are going to get a head every time. So that was a biased coin. Here I am using another form of biased coin which doesn't give you head always. It gives you head 25% of the times and gives you tail 75% of the times. And again what I am going to do is, then again I will have these 4 experiments here. For each experiment I am going to toss a coin, and then if I get an head, I infect the particular node. If I get a tail, I do not infect the particular node. And here what do you think is going to be the expected number of heads? So it's again very simple. It's almost the same what we have done previously. So again we take 4 indicator random variables here, x1, x2, x3 and x4, and we know that expected value of x is expected value of x1 plus x2 plus x3 plus x4, which can be written like this. And we have looked at what is the expected value of a indicator random variable is nothing but the probability of 1, which is probability of head, which is 0.25 in this case. So I'm going quite quickly because it is similar to what we have done previously. You can pause the video here and see what is actually happening. So we get here 0.25 into 4, which is nothing but 1. So the expected number of heads here is 1, which means that if this guy here infects each of these nodes with a probability 0.5, on an expectation, on an average, it will infect one of its children. Okay. Now what we are going to do is, we are going to generalize what we have done till now. So we have looked at 2 examples, and now we are going to generalize whatever we have done, and it is very easy. How do you generalize it? I take a network here, and now I say, instead of having, let's say, 4 children, so instead of every node having 4 children, I say that every node is having k children, or k, not neighbors. Every node is having k children. So the node here, it will have 4 children, and then the node here, it will have its own 4 children, node here 4 children, and so on. I'm very sorry, not 4, it will be k. So this this node here will be having k children, this node here will be having k children, this node here will be having k children, and so on. And let's say the probability of infection is p. So we have taken 0.5 in the first example, 0.25 in the second example. Here we generalize it and take this probability to be p. Now what do you think will be the expected number of infected people? So it will be simply be So you can write each of these. So how many experiments are we doing here? We are doing k experiments here because there are k children. And what is the probability of success in every experiment is p. So the expected value of x, that is the expected value of infected people here, is going to turn out to be p plus p plus p k times, which is going to be equal to p into k.